Ever wondered how data flows within a system? Today, you'll find out. Let's dive into the world of data flow diagrams, or DFDs as they're commonly known. DFDs are graphical tools that help us visualize and understand the flow of data within a system. They are widely used in systems analysis and design, helping analysts and designers to get a clear picture of the system's structure and behavior. They are particularly useful in identifying data transformations and interactions, and in effectively communicating system requirements. So, what are the key components of a DFD? 4 elements stand out: processes, data flows, data stores, and external entities. Processes, depicted as labeled rectangles, represent functions or transformations performed on input data to produce output data. They are the actions that take place within a system. Data flows, on the other hand, are represented by arrows. They show the movement of data between processes, data stores, and external entities. They are the lifelines that carry data from one point to another within the system. Data stores are where data is persistently stored. They are represented as rectangles with labels that describe the type of data stored. Think of them as warehouses or repositories within the system. External entities, also depicted as labeled rectangles, represent sources or destinations of data that interact with the system. They could be individuals, organizations, or other systems that provide or receive data from the system under consideration. Understanding and correctly using these components is key to creating an effective data flow diagram. They help depict the system's processes, the movement of data within it, the places where data is stored, and the external entities that interact with the system. In essence, DFDs are graphical tools that help us visualize and understand the flow of data in a system. Whether you're a seasoned software developer or just starting out, mastering the art of DFDs can prove invaluable in your journey to understand and design complex systems. So, what exactly does a process in a DFD represent? Let's dive right in. In the realm of data flow diagrams, a process is essentially a transformative function. It takes in data, performs a specific operation on it, and then produces output data. Think of it as a kitchen blender, where raw ingredients come in, get blended, and out comes a smoothie. In a DFD, this transformative function is represented by a rectangle, bearing a label that succinctly describes the operation being carried out. It's a bit like a name tag that tells everyone what this process does. For instance, it could be order processing, payment verification, or inventory update. Processes are crucial elements in a DFD because they are the active components. They are the ones making things happen, the gears that keep the system running, if you will. They transform data, pushing it from one point to another, enabling the system to function effectively. So to sum up, processes are the actions that transform data within the system. Next up, let's delve into data flows. Picture data flows as the highways of our system, facilitating the smooth movement of data from one component to another. They're the backbone that connects processes, data stores, and external entities, allowing them to interact and exchange information. In the graphical language of data flow diagrams, data flows are represented as arrows. These arrows serve a dual purpose. They not only illustrate the route that data takes, but they also indicate the direction of that movement, whether it's flowing from a process to a data store, between two processes, or from an external entity into the system. The arrows guide us along its path. An interesting aspect of data flows is that they can represent a single data item or a set of data items that flow together. So, in essence, data flows are the arteries of the system, carrying data from one point to another. Now let's talk about data stores and external entities. Data stores are the memory banks of a data flow diagram. They're where data is stored for later use, acting as a sort of repository for information that's been processed and will be needed again. In the visual language of DFDs, data stores are represented as rectangles, often with a flat side, which makes them look like two-dimensional versions of real-life storage boxes. Inside these boxes, labels describe the type of data held within. External entities, on the other hand, are the lifeblood of a system. These are the sources or destinations of data that interact with the system. They could be users, other systems, or organizations, anything that produces or consumes data. Just like data stores, external entities are also depicted as rectangles in a DFD. They're labeled to indicate their role or identity. Together, data stores and external entities form the boundaries of a system. They're the starting and ending points of data flow, the in and out boxes of a system. Imagine a library system. Here, book records would be a data store, holding all the information about the books in the library. Librarian and member would be external entities. The librarian might check the book records data store to find a book for a member, and the member might update the book records when they return a book. But it's not just about storage and interaction. Data stores and external entities also help us understand the scope of a system. By identifying the external entities, we can see who or what interacts with the system. By identifying the data stores, we can understand what kind of information the system handles. In a nutshell, data stores and external entities are vital to understanding the overall context and operation of a system. They provide a clear snapshot of where data comes from, where it goes, and where it's stored in between. They help us visualize the boundaries of the system and understand its interactions with the outside world. Data stores are where data rests, and external entities are where data begins or ends its journey. Now that we've covered the components, let's look at the bigger picture. Just like assembling a puzzle, once we have all the pieces, we start to see the whole image. In the world of data flow diagrams, our completed puzzle takes the form of context and level 0 diagrams. A context diagram is our map, our highest level of abstraction. It's like viewing the Earth from space. From this vantage point, the system is depicted as a single process, surrounded by external entities. It's our bird's eye view, giving us an overview of the system and how it interacts with the world around it. Now, imagine we're zooming in, getting closer to the ground. As we move in, we begin to see more detail. This is where the level 0 diagram comes into play. The level 0 diagram is our first layer of detail, our first step into the system. It decomposes the single process of the context diagram into multiple processes, each with its own data flows and external entities. This is our top-level detail, showing us the primary processes of the system and how they interact with each other. Just as an architect uses blueprints to understand a building structure, we use the level 0 diagram to understand the structure of our system. It's the first step in understanding the system's workings, breaking down the processes into manageable chunks. So, think of the context diagram as our satellite image, our broad overview, and the level 0 diagram as our street view, our first glimpse into the system's inner workings. Together, these diagrams provide a comprehensive overview of the system. They allow us to understand the system at different abstraction levels, from the high-level overview of the context diagram to the detailed processes of the level 0 diagram. In essence, context and level 0 diagrams are tools that help us understand the system's structure and how its parts interact. They give us the ability to see the system as a whole and also to zoom in on its individual processes. Context and level 0 diagrams help us grasp the system at different levels of abstraction. Finally, let's explore two key concepts in data flow diagrams: decomposition and balanced decomposition. Decomposition is the process of breaking down higher-level processes into smaller sub-processes. This is like taking apart a puzzle to understand each piece individually. It gives us a more detailed understanding of the system, letting us see the finer details of how data flows and processes interact. On the other hand, balanced decomposition is the principle that each process in a DFD should have roughly the same level of detail and complexity. Imagine trying to solve a puzzle where some pieces are much larger than others. It would be confusing, right? That's why we strive for balance. It helps maintain consistency and clarity in the diagram, ensuring that every part of the system is equally understood and represented. Through decomposition, we break down complex systems into understandable parts, ensuring balance along the way. So, what did we learn about data flow diagrams? We've seen that these graphical representations are crucial in systems analysis and design, providing a clear picture of the flow of data within a system. We've explored the core components of a DFD: processes, data flows, data stores, and external entities, each with their own unique symbol and role in the system. We also delved into the concepts of context diagrams, offering a high-level view of the system's interactions with external entities, and level 0 diagrams, providing a more detailed look at top-level processes and their interactions. We learned about the importance of decomposition, breaking down higher-level processes into smaller sub-processes for a detailed understanding, and balanced decomposition, ensuring that each process in a DFD has a similar level of detail and complexity for consistency and clarity. Remember, a well-drawn DFD can be a powerful tool for understanding and communicating about a system. Happy diagramming!